In the learner's big book, today we are going to learn about spectroscopy and its principle under spectrophotometer, how it is going to work, where we know that spectrophotometer is an instrument for measuring the absorbance of a solution, where the absorbance is a useful quantity which will be studied under Beer's law of spectroscopy with the help of the formula absorbance is equal to epsilon Cl and absorbance is equal to epsilon Bc. So what are these formulas and the Beer's law, what it is going to state, we are going to study in the following slides. Now spectroscopy comes under the word the spectrum, that is the multiple colors which we are going to see when the white light is going to be scattered. That white light will be scattered by using a prism. So we know that the white light is going to scatter in the form of the waveguide. This waveguide is going to have the different wavelengths, that is the swab of wavelengths from 0 to 5000 plus nanometers. Now here spectroscopy originated through the study of visible light dispersed according to its wavelength by a prism. So these both are the definition. This definition is also going to holds good, and even this definition is also going to holds good. So here the spectroscopy is going to signify multiple wavelengths of light. So in totally we are going to understand that spectroscopy is nothing but it is going to signify or indicates the multiple wavelengths of light which will be through a particular medium, where we are going to see the study of the interaction between the matter and the electromagnetic radiation. Multiple wavelengths are always the electromagnetic radiations which are going to get through the matter, and they are going to show the absorption and the presence of the matter within that particular solution medium. So electron spectroscopy has been observed, atomic spectroscopy has been observed. So depending upon the kind of the components are observed, according to that the spectroscopy has been described. But here we are particularly discussing regarding with how the spectroscopy has been applied in the spectrophotometer. So here in spectrophotometer, the spectroscopy and the Beer's law is going to play as a principal role, so that we are going to discuss it in the further slide. Now Beer-Lambert's law, it also called it as the Beer-Lambert law, Lambert-Beer law, Beer-Lambert-Boggart law. So these are the three different names which are commonly used to call this particular law. So according to this law, it states that quantity of light will be absorbed by a substance dissolved in a fully transmitting solution is directly proportional to the concentration of the substance in it and the path length of the light through the solution. Now here, as we have discussed, the spectroscopy is having the different color emission, that is the spectrum, and the spectrum is because of the different wavelengths within that particular light, and it is the electromagnetic radiation. When you are going to subject a particular quantity of light, that particular quantity of light is going to be get absorbed by the substance present in the solution, but provided the solution should be the transmitting solvent. The solution always should be the transmitting solvent. So the substance dissolved is directly proportional to the concentration. Now the law is explaining that it is the quantity of light absorbed when it is going to pass through the transmitting solvent, and whatever the light has been passed, it is going to be detected by the further detectors. So that is going to be calculated according to the path length. That is going to be calculated according to the path length and the concentration of the substance has been dissolved. So here further the whatever the amount of the solute has been or the substance has been dissolved in this transmitting solvent is going to be calculated. Now here the key takeaways of the Beer's law is that the concentration of a chemical solution is directly proportional to its absorption of light. Here they have simplified the law. Now chemical solution means here the substance which is dissolved in the transmitting solvent, both together is called it to be as the chemical solution. Here what is taken in the equate, this complete solution is the chemical solution, which is having both the dissolved substance and also the solvent. A beam of light becomes weaker as it passes through the chemical solution. The reduction of light occurs either as a result of distance through solution or increasing concentration. Now here, when a beam of light is going to be passed, because of that the reduction of light is going to occur. Reduction of light is after passing through the transmitting solution. So here, whatever the light seen here, that is the reduction of light. Whatever this light seen here is the complete light or the wavelength of the light. So here, whatever has been passed, it is the reduction of light as a result of distance through solution. Now here, from here to here, to the incident to the final path, this is the distance which has been passed through the light, which is going to strike through the transmitting solution or increasing concentration. If there is a decrease in the light, there should be the increase in the concentration. In the sense, whatever the concentration is present in this solution is going to reduce the light which is going to pass after it is going to pass through it. That is what the meaning. Now, this is the Beer's law formula. A is equal to epsilon BC, A is equal to epsilon CL. Both are the same formula, but use of the variables are different. So why I have used this both varied form of the same formula is to make you sure that there may be other forms of this also, so that no need to get confused about that. If you are going to get even this kind of formula or this kind of formula, both are going to remain same in their explanation. So here, in the place of B, L has been used. So there will be the change in the position or the variable of the B or the L. In some book there can be the any other character has been used. So you should be very clear that before you should not get confused if the examination is going to get the formula with the different variable. So here, where A is the absorbance, here also the same. Epsilon is molar absorptivity with units of length per molar per centimeter. Here also epsilon is the extinction coefficient for the compound at that wavelength in per molar per centimeter. So here these both are the same explanations. So you no need to get confused. Here length per molar per centimeter. Here also the wavelength per molar per centimeter. Now when you are going to consider here, when a particular wavelength has been passed through this wavelength is going to differ further after absorption. So here whatever the compound is present, and that will be having a particular molarity, and it is going, this particular molarity is going to be present, it will be considered to the per centimeter. So that is what the meaning of this per molar and per centimeter. So here B is the path length of the sample using expressed in centimeter. So here B is the path length, and here L is the path length of the solution in centimeter. So as I told that B and L are the only the different characters, but the explanation is of the path length. Now further is C. C is the concentration of the compound in solution expressed in per molar length. Here also it is the C is the molar concentration of the absorbing species. Here absorbing species is the compound. Now when you are going to consider molar absorptivity extinction coefficient, here molar absorptivity is that each compound is compound in the sense, if you are going to consider the different compounds, let it be proteins In the proteins there are many amino acids. In carbohydrates there are many carbohydrates like glucose, sucrose, fructose, and different compounds, chemical compounds. All these compounds are going to have a particular absorptivity, molar absorptivity at particular wavelength of the light. So here, under the overall spectrum of the magnetic radiation, which is going to have the different wavelength, within this wavelength we cannot measure the absorbance at our willing nanometer wavelength. So here it is said to be that the particular wavelength will be going to be a molar absorptivity wavelength. So that wavelength is going to act as the reference for the estimation of the absorbance of any compound. So here when you are going to consider molar absorptivity, also known as the molar extinction coefficient, measures how a chemical species absorbs a given wavelength of light. Molar extinction coefficient is a measure of how strongly a chemical species or substance absorbs light at a particular wavelength. Now here, when you are going to subject a particular compound within a wavelength of 250 nanometer to 500 nanometer or 900 nanometer, at a particular point, the absorption of the particular wavelength by the particular substance is going to show the peak. So here, under that, if you are going to consider, so we will consider this green curve. This is for phenylalanine amino acid. Under this, you can see this is going to be subjected under the absorption from 200 nanometer to 300 nanometer. So here at the 200 nanometer and after, it is showing the increase in the peak, rise in the peak. After the about 215 or 217 or 218 nanometer, the fall of the peak is taking place. So here between 200 to 225 nanometer, there will be the absorption of this particular phenylalanine. In the same manner, tryptophan, tyrosine and bovine serum albumin is going to act. Now here you can see. Now as per this particular, with reference to that particular curve graph, the extinction coefficient is nothing but a chemical species or substance absorption light at a particular wavelength is always constant. So here the same molar extinction coefficient has been put in the molar absorptivity. So it measures how a chemical species absorbs a given wavelength of light. So these are the two different names has been given for the same explanation. Now here, what is molar? Molar is the molar concentration of a chemical species. Let it be a biochemical species, organic species or inorganic species. Let it be any kind. Though that is the particular concentration, it can be called as the amount of concentration or substance concentration. So you know that the substance concentration can be measured under molar, so as per their chemical formula, and further it can be studied. Now here we have taken an example of the Beer's law formula, where we are going to subject a sample. We have not mentioned a particular chemical species here, but just for the understanding, we have taken this example where we are going to subject this sample at 275 nanometer, and we are going to get the reading of absorbance of 0.70, and we know that the molar absorptivity of that particular chemical species sample is 8400 per molar per centimeter. So here the cuvette is of 1 centimeter width. The length of the cuvette is always constant, that will be 1 centimeter. So here that is what the cuvette length. What is the concentration of the sample? Now here, as per the absorbance and the molar absorptivity and the length of the cuvette, we are going to take the readings and we are going to subject under formula, Beer's law. Now here point absorbance, at the absorbance 0.70, that will be subjected at the epsilon 8400 per molar per centimeter will be subjected, and length b is the length, that is 1 centimeter, will be subjected, and C is to be calculated, that is the concentration of the substance. So C is equal to 0.70. So these two values goes to the denominator. So C is equal to 0.70 divided by 8400 per molar per centimeter into 1 centimeter length is equal to C is equal to 8.33 into 10 to the power of minus 5 molar per length. So here per length in the sense the each centimeter within the cuvette is having the 0.33 into 10 to the power of minus 5 molars of this sample as per this particular absorptivity is going to be present. Now I have taken a chart after a long struggle. Now here you can see different chemical species. Now you can see common pigments to all three domains of life. They are given absorbance maximum in nanometers, molar extinction coefficient, that is again called to be as the molar absorptivity or molar absorption. Now here adenine always show the rise in peak, that the 261 nanometers. So its molar absorptivity or molar extinction is 13,400. Guanine can be measured at 243, 272.75, and their absorptivity is these two readings. Thymine at 1, that is 264, and this is the molar absorptivity. Cytosine, this one. Uracil, this one. Like this there is a list of the all chemical species. So you can go through this particular list. Here we are going to study how spectroscopy has been subjected in the spectrophotometer. Spectrophotometers are the means of the measurement, that is an equipment, but under that the spectroscopy principle, that is the Beer's law, is going to function. Because of that we are able to get these particular absorbance values, and we are able to calculate a particular compound concentration, molar per length. Now here spectrophotometers have the ability to measure absorbance at specific wavelengths. Now here they have been manufactured in such a way that the technique allows the spectrophotometer to emit the light of particular wavelength, and because of that it will be very easy for the estimation of a particular substance at that particular wavelength, and we can record the absorbance. Actually in spectrophotometers there will be a component called monochromator, which is of either of the prism or of the diffraction grating. Now that is placed here. The first component will be the source, the next component will be the collimator, that is a kind of the converger of the source light, and it is going to create a beam of light here, so that it is going to pass through either the prism or the diffraction grating. This prism or diffraction grating is going to create a spectrum, and the spectrophotometer has been designed in such a way that out of this spectrum a particular desired wavelength can be passed through the wavelength selector. Because of this the particular wavelength of our desired nanometer is going to pass through the sample solution, and further it is going to give a particular absorbance reading. Now here as we know that each component is going to have the extension coefficient, according to that the particular absorption is going to takes place. So each component is having the spectrum absorptive, that is the molar absorptivity value. According to that a particular wavelength has to be selected. So depending upon the particular limitations of that component, we can make adjustment in the spectrophotometer. So this is what the particular significance of the spectrophotometer. Now in the next slide, we will discuss the how the absorbance has been calculated. So absorbance allows us to calculate the concentration of compounds in solution. Another definition is that absorption is a measure of capacity of substance to absorb light of a specific wavelength. It is equal to logarithm of the reciprocal of the transmittance. So here, what is transmittance? It is whatever the wavelength has been passed through this. After that, whatever the wavelength, whatever the intensity of the light has been detected by this particular detector. This is called to be as the transmission, where IO is the amount of light entering the sample here, and I is the amount of light leaving the sample here. Absorbance is therefore a measure of portion of light leaving the lamp that actually makes it to the detector. Now here, when the light is being left the lamp as an incident light and it passed through here, whatever the light has been absorbed by the compound is the absorbance. Now when we are going to consider here, the detector is going to detect this particular light which has been coming after the absorbance has been taken place. So what we are going to get as the absorbance is the logarithm of the IO and I. Here you can see the formula. A is equal to log IO by I. IO is the incident light, I is the final light which has been detected. So the logarithm of this is the absorbance what we are going to get. A little thought will reveal that when absorbance is equal to 1, only 10% of the light is reaching the detector. Now here always we are going to measure the absorbance for different chemical species or the components. We measure between 0 to 1 or 0 to 2 depending upon the opacity of that particular compound. Opacity in the sense, if the compound itself is an indicator or an indicator has been used in the compound. Depending upon that particular compound indicator, thickness in its or darkness in its dye or the color, the absorbance is going to increase within the compound during the light is going to pass it through it. So here when you are going to consider the absorbance value, that is the logarithmic value is up to 1, then the light which is detected by the detector is 10%. Here at the IO it will be 100%. After passing through this QET sample, the light is going to absorb it up to 90%, and the left light towards the detector is of the 10%. So when absorbance is 2, only 1% of the light is reaching the detector. So here there is no light has been left after the sample. So there is only 1%, that is the negligible amount of the light. So in the sense, the absorbance value is not the correct value what you are going to get at the value of the 2. So the absorbance values what we are going to get, it is measured between 0 to 2. So if you are going to get the value below to 1.5 or 1 below to 1 is very good. Below to 1 is more better compared to the above to 1. If it is near to 2, you have to dilute the sample and you have to use. Diluting in the sense you have to dilute the whole grid of samples from blank to the sample. In the sense, if you are going to consider protein estimation by the Loris method, in that there will be the 4 to 5 standard samples or the standard concentrations and also the samples. So all you have to dilute with a particular dilution. So after that you have to measure this particular sample again. So here now we discussed both formulas, that is one as this one A is equal to ECL, that is these three components, and A is equal to log IO by I. This is also with the single component, that is the incident light and the emitted or the left light of a particular wavelength or a radiation of particular wavelength. Now this particular formula has been compressed to this particular formula where the calculation is very easy. This formula is used in the spectrophotometer where it is going to completely depict the Beer-Lambert's law formula. So it is going to give a particular brief explanation of how does a spectrophotometer is working, and with the help of this how we are going to calculate the absorbance. Next, so precautions to be taken during the absorbance. So here if the readings is greater than 2, dilute the sample and repeat the measurement. Spectrophotometers measures the decrease in amount of light reaching the detector. There can be because of the interpret fingerprints. When you are going to use or handle the cuvette is going to get the fingerprints on it. Because of that, light is going to get diffracted. So, or air bubbles present in the cuvette or any floating objects which is going to present in the solution. In the sense, any debris which is going to float within the solution, it can give the diffraction of the light. So you therefore need to look carefully at your cuvette before putting it into the spectrophotometer to make sure that your reading is not subject to these types of artifacts. So here it should not be any disturbance so that you can get a particular absorbance value, so that it should be accurate. Cuvettes are usually square objects 1 centimeter across. In some case the liquid reservoir is not square. In those cases, make sure that the 1 centimeter dimension is aligned with the light path. Now here you can see in this particular cuvette, here there is some designs. We should be very sure to keep the 1 centimeter dimension aligned to the light path. So here how they have been shown. In the same manner you can go through your lab spectrophotometer manual, how it has been shown. In that you can get through it and you can place the cuvette. Some cuvettes are designed for visible light. Here we should be very careful. When the spectrophotometer is set for ultraviolet wavelengths, make sure that your cuvette does not have a large absorbance when it contains only water. So here we will discuss in the next slide. Now cuvettes has been differed per their material, like plastic and the glass. Plastic cuvettes will be used for once. Glass cuvettes can be used multiple times. Why we have to use plastic cuvettes only once? It is because they are going to get scratches on them. Because of that you cannot use it more number of time. So because of the scratches, the diffraction of the light may takes place. Because of that, the absorbance values may differ at large errors. Glass squids are not like that. Glass squids are not going to get any scratches, and also you can wipe the fingerprints very easily and you can keep it clean as per the guidelines given in the manual. So here the name of this particular quets as per this particular visible or the radiation wavelength. Now if it is VIS, it is called to be as the visible range quets. If it is UV VIS, even for the ultraviolet range and visible range, for both we can use. If it is the IR, it is the infrared range. So here you can see the quets. If it is the polystyrene, it is for visible. If it is acrylic, again it is for visible range. UV plastic, UV and the visible range. Optical glass for visible range. UV quartz for both visible UV and visible range. IR quartz, it is for all three ranges, and sapphire for all three regions. So here the range you can see, it is from 340 nanometer to 900. So the wavelength differs with the different kinds of the quets as per the radiation. Now here it is from 340 to 5000 nanometer is the range. Now you can see UV 315 to 400 nanometer, it falls here. Now it is 250 to 5000 nanometer, it is from here to here. So from here to here. So like this, there are different radiations or the wavelength within this particular spectrum. Now I hope you have understood how the quets has to be used. Now if you are going to consider this particular chart, you can see that each and every chemical species is having its own absorptive wavelength. Here it is for phenylalanine. Here the tryptophan is the blue. Now the tryptophan, this one, TRP, it is showing two peaks. One is here, one is here. When the chemical species showing two peaks at different wavelengths, this is the different wavelength and this is the another wavelength. Out of these two, one you can consider, provided one or two, both you can consider, provided the both should not exceed the value of 2 absorbance. Because as we have discussed, the value of 2 absorbance is that there is no light is detected by the detector of the spectrophotometer. So here this particular wavelength of the this particular peak of the tryptophan is neglected because it has been seen about to the absorbance value of 2. In the same manner, the tyrosine, here it is also having 2 peaks. One will be neglected, another will be considered. So 275 nanometer. Here also for the tryptophan 275 nanometer. For bovine senile albumin at 225, it is showing the very high peak 2.5 absorbance. It is wrong. So bovine serum albumin is also showing the peak at 275 and across. In the same manner, if you are going to consider this graph, here we have not mentioned any samples name, but we are given anonymously. So when you are going to consider the sample A, it is 1.5 and above. Sample B, it is more than 2. Sample C, it is just below to the 2 absorbance. Sample D is at the 0.5 absorbance. Now here the compound which has been used is showing a compound D is showing a good absorptive value at 310 nanometers, whereas the other compound, the A, is showing the absorptive value at 1.5, that is the absorbance, but the compound B is showing about 2, so we are not going to consider. So this is how the chemical species are going to show the difference in their absorbance when it is subjected under a particular swab of wavelengths. So I hope I have given a little clear explanation, and I did not go deep in the explanation because I don't want to make a lengthy video log. And if you have any questions or doubts regarding my explanation, you can ask in the comments below, and I ask you to spread these particular slides among your friends and give the feedback on this particular video logs. Thank you.